Okay, so in this lecture, uh, we are actually trying to do a review of single variable optimization, which is something we have already learned in our high school. So this is just like a recap of what we already know, so that going further, we can extend these ideas to multi-variable optimization problems. Okay, uh, so single variable optimization is relatively simple, uh, and let's see what happens. So here mostly we are considering, even though optimization problems can have maximum and minimum, here we are restricting our analysis mainly to minimization problems. That too, we're trying to find a global, sorry, no, a local minimum rather than a global minimum. So yeah, let's move further. Okay, first of all, we know what is a minimum of a particular function. Okay, I hope. Okay, for let me just define the minimum of function also, just for the sake of completeness. Yeah. So we have a function. Let's first define what is a minimum of a function before we understand how to find the minimum. Okay. Yeah. Let's give a definition of a minimum. So let's start with the global minimum first, because um, so that is the absolute minimum of the strict, or the strict minimum of that particular function. For the entire function, that is the point which takes the lowest value. Okay, what is the definition of a global minimum? How do we define a global minimum? So a point x star is a global minimum of a function f of x. This is a one-dimensional function. Right now we are considering x as a single dimensional variable. If f of x is greater than or equal to f of x star for all x in the domain of the function f of x, or all x belonging to the real line. Okay, here we are assuming f of x is a function from R to R. So what does this mean? It means, let's see, uh, we have a function which goes something like this. Okay, and yeah, it extends all over the real line, but right now we have just taken a snippet of that function, which taken up the value of the function in a particular interval, and see how it is going. So, just by visually inspecting, we know that the value of the function is varying. It's not constant, or it's not uniformly spread out through the entire domain of the function. But by visually inspecting itself, we can understand that this is the lowest point of the function. This is the lowest point of the function. This also looks like a lower point, but this one is actually lower than this particular point. So this one we can call as the x star. So if you take any, this is our x-axis, and normally we plot f of x along the y-axis. So if we take any, for any x other than this x star, if we take the corresponding value, suppose I take my um, x to be here, this is my x1. Okay, and let me take another another x2 here, x2, and for that corresponding there is an f of x2. For this there's corresponding x1. So if we take any x, then their corresponding f of x will be always less than uh, the value of f of x at x is equal to x star. This is what we call as the global minimum, right? So here, this, even though it's a global minimum, we are defining it as uh, less, I mean, f of x greater than equal to x star. Yeah, instead of this, if we are taking the condition where f of x is greater than f of x star, this is known as a strict minimum. Strict minimum in the sense there is only a single point which is acting as a minimizer. But here we have the leniency of multiple points acting as a minimizer. Okay, yeah. This is actually what's the definition of a global minimum. Then let's take what happens, what is actually the condition for the definition for local minimum. Okay, so in local minimum, the idea is confined to a particular interval. We are not looking at the entirety of the domain of the function. We're just looking at a particular interval of the function, particular locality of the function. For example, if I'm looking within this range, then let's call this as yeah, let me call this point as x star. Then this is like x star plus epsilon, x star minus epsilon, where epsilon is an arbitrary positive quantity. So we are looking just within that particular locality. In that locality, if the above condition holds, if in that particular locality, if uh, if f of x is greater than equal to f of x star, where should it be? For all x belonging to R, but there's a caveat, satisfying x minus x star should be within a particular interval. It's within a range, right? Or we can say x is equal to x star plus epsilon and x is equal to x star minus epsilon. Okay, in that range, if all the values of the function is greater than or equal to the value at a particular point, then that point can be considered as a local minimum. Right. Similarly, like we have said earlier, we can also, if we change f of x greater than f of x star, it will become a strong minimizer. Okay, so this is actually the idea of a minimum in a function. So once we have this idea, so by definition or by visually inspecting, we can see this. But now we have to find a rigorous mathematical way of identifying or reaching to the minimum point of a function. For this, we use the idea of derivatives. And using the derivatives, we perform some tests to see what conditions are satisfied by this. Are there some special characteristics of this minimum point? Either it is locally minimum or globally minimum. And using that, we're trying to understand we are trying to identify the minimizer or maximizer of a function. Okay, so in our case, we are more interested in the minimizer. So right now, we have understood what is a local and global minimum of a function. And the next lecture, we'll try to understand how um, we identify this local and global minimum points. Okay.